Welcome to lecture number 7. In this lecture, we're going to finally introduce what is known as a random walk. And like I was saying, that this is basically the only thing we study the entire semester. Now, later on, what we're going to do is we're going to generalize this in different ways, but it will feel like it's the same thing, but there's some changes in what we're studying. So that's why I say that even though you can call this class the study of stochastic processes, most of everything what we're doing is going to be some form or another a random walk. And there's a lot of interesting things you can say about them. And today we're going to introduce what the random walk is. Let's start with this. First, it would be helpful to give an idea of what we're doing. So we're playing a game. We're going to play a game. And this is going to be a stochastic game. The word stochastic in Greek means random. This is going to be a random game. So the simplest random game is when you have two outcomes. So you have a coin, you have a fair coin, and you have two outcomes, heads and tails. And the game is very simple. You will gain $1 if it comes out to be heads, and you lose $1 if it's tails. So that's the game. So you start at 0, and then you throw a coin and you randomly move to either 1 or -1. Let's say you move to 1. And then you just play the game again. You throw the coin and then you randomly move to the left or right. So you could get 2 heads in a row. And when you throw it again, maybe this time you go back. You go back, you go back. Then you go forward, and you go back. And you can see it could potentially become quite complicated the longer you play the game. That's the idea. It is also helpful to visualize. Oh, and by the way, this is why we call it a random walk. You're randomly moving, right? You're randomly going on a walk, and every time you take a step, you either go left or right. So this is one way to visualize it. The other way you can visualize it is you can plot this random sequence where this is time, and time just represents what stage in the game you're at, and this is the amount of money you've gained or lost. So you start at 0, and then at the next stage you either go up, maybe you go up, you go down, you go up, down, 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 you can go down, up, whatever. And so like in general, it could be some kind of really complicated type of a sequence that you form out of that. And that is a random walk. And I'm also going to show you some simulations how to do it. But first, let's just define a random walk rigorously. So here's the rigorous definition of a random walk. Let xn be a sequence of independent random variables so that, and I know I've said this many times before, but I have to keep on saying this over and over again because it's so important. In probability theory, we usually work with random variables. There is a sample space hidden in the background, and that's the foundation for the theory, but we often do not even reference it unless we really, really have to. So this is often the way we do probability theory. We just assert some random variables that have certain properties, and then we just move on from there. The sample space will not be necessary. So we're going to have a sequence of independent random variables so that the distribution of each one is discrete. It's delta -1, delta 1, and it's an even mixture, right? Evenly mixed between those two. So in other words, i.e., each xn is a discrete random variable, and it has 2 possible outcomes. So these are random variables on our sample space into the real line, except we're not even talking about the sample space, but what we're saying is the value of each of these random variables will produce 2 possible outcomes, -1 and 1, plus or minus 1, with equal probabilities. That would just mean the probability that xn is equal to plus or minus 1 is exactly 1/2. Just a few things I want to say. Some of you might be thinking, did we not say that the probability that a random variable takes on a specific number happens with probability 0? That is true when you're talking about random variables that are absolutely continuous, because then you're just integrating over a single point, and that happens with probability 0. But when you're working with discrete random variables, then the probability that they take on a particular value could be a positive number. Also, the meaning of this, if you're wondering what this means, is so the probability that xn is equal to, let's say, plus 1. It's the same idea for the other number. That's just another way of saying this is the probability of the event. So this is going to be the collection of sample points in the sample space, so that xn of omega is equal to plus 1. That's really what we're saying. Or if you prefer, this is the pullback of the singleton set 1. It's just tedious to write this out. This is just what this means. You're going to look at all of the sample points on which the random variable takes on the value plus 1, and the probability of that event, it's going to be an event because you're pulling back a Borel set, and by definition, a random variable will pull back a Borel set into the sigma algebra. So you can calculate the probability of whatever that event is, and the probability of that event will be exactly 1/2. We just never bother to write this because that's fairly difficult, and then we have to reference back the sample space. So it's more convenient to just leave it like this, but that's the meaning of that. So these are discrete random variables. This is their distribution. So they have two possible outcomes, plus 1 and minus 1, and they happen with equally likely probabilities. And that's exactly what we were saying. You want to intuitively think of these, like intuitively, this is a sequence of coin flips, where you just flip a coin over and over and over and over again. That's what that is. That's just a sequence of coin flips. But instead of calling them heads and tails, you rather call them with plus and minus 1. That's what you're doing with equal probabilities. And then we define Wn. So we define, let me go back. So for each natural number, so natural numbers start at 0. So our sequence, it starts at 1, but natural numbers, they start at 0. So for each natural number, we construct a random variable, Wn. Intuitively, this is going to represent, so intuitively, this is the random walk up to time n. That's what that's supposed to represent. Random walk up to time n. As follows. So we're going to define W0 to just be equal to 0. So this is a random variable, by the way. I know you can say it's not really random because it always gives you 0. But under our definition of a random variable, it's just a function on the sample space. So this is the function that assigns the value 0 always. That's not very interesting. But for n greater than or equal to 1, we define Wn to be equal to the sum of the first n Wn is the sum of the first n random variables in the sequence. So what we understand is that every one of these random variables, they give you plus or minus 1 at random, and you're summing them up. So at the very most, all of them are plus 1, and then Wn is equal to n. And at the very least, Wn, all of these are negative, and then you have negative n. So that's what Wn is. It represents that. So this is the way you define a random walk. Now, there is a theoretical question that we're going to address later on. We're not going to talk about it for the moment because it's going to interrupt the flow of the class. And the issue is the following. How do you know that such a sequence of independent random variables even exists in the first place? Because in the definition, we're just proposing that we have such a sequence of independent random variables. How do you know there is such a sequence? Intuitively, it does make sense. You have a sequence of infinitely many coin flips, but maybe there's something pathological that happens when you consider infinitely many coins. So maybe such a sequence with such a property does not exist. So that is something we have to justify. We have to justify the existence of such a sequence. But let me show you some code to simulate this on a computer. So for those of you who have seen the previous lecture, I mentioned that I'm going to be using something called POSIT Cloud. You do not have to install anything, and it is free to use. You can use a very simple account that has limited computing potential, but for the purposes of this class, it would be perfectly fine. You do not need a lot of processor cores. You do not have to buy the advanced version that is faster. This is going to be good enough for us. So you make yourself a free account. It's pretty self-explanatory. Then you log in. When you log in, you have to create something called a workspace. I'm not even going to show you how to do that because that would insult your intelligence. You can figure that out. And then when you get to the main page, you can say your dashboard. There's going to be an icon that says create a new project. And when you create a new project, it's going to load something like this. That's what it's going to look like. Except I moved mine away, so that's going to be your project name. I called it Random Walks. Actually, I think you're going to have a bunch of text over here, but you can clear away the text by clicking on this broomstick in the upper right corner. And if you click on it, so if you type a bunch of stuff over here, you move it, you clear it away with the broomstick. I'm just saying it in case we have some new viewers who did not see the previous video. Then you will click on File, New File, and select R Script. And this is the window where you're going to do your code, and this is the window that's going to show you the output. So if you want a certain answer, this is where you see it. Now, how do you create a sequence of heads and tails? So you use the sample command. I went over this in more detail in the previous one, but I'm going to give a very quick explanation again in case we have people who are watching this without seeing the previous one. So you write sample, and then you need a collection of numbers to sample from, to choose random samples from. The way you write it is you use the letter C. The letter C stands for combine. This is what you want to do if you want to create a list of numbers. So the numbers we're going to be choosing from are the numbers -1 and 1. And then how many numbers do we want to write? As you can see, I have a pop-up icon. It asks for size. Size is equal to 1. So if I select this and I click Run, it will randomly choose a number between 1 and -1, and by default it chooses with equally likely probability. If you want to change the probability with how it chooses the number, then you have to modify that a little bit, but by default it's equally likely. So if you have to select that entire line, and then you can click Run, and it will produce a number for you, 1 or -1. Now, some of you will get 1, and some of you will get -1 because we're using a random number generator. Now, I want to quickly remind you that all random number generators are really pseudo-random number generators. They need an initial condition to start with, and the initial condition that they start with depends on the time at which you load the software. That determines the initial condition, and from there, the random number generator completely determines every number that follows. It just looks random, and it behaves as if it is truly random, and that's why we use it, but in actuality, it uses an algorithm to do it. To set the random number generator so that we always produce the same number, we have to write set seed. So you need an initial condition. So today's date is August the 7th, so I'll just write this as August 08, 07, so 807, let's set that as our seed. And now if you run this, so let me do it like this. I'm going to first run this. That sets the random number generator, and it will determine the same numbers for all of us. And then you select this. And now if you click Run, we all get the same number, -1. If you click Run again, we get -1. If you click run again, this time we get -1. You click it a fourth time, now we get 1. And if you if you keep on clicking run, it will randomly choose numbers 1 and -1, and we're always going to be choosing them in the same way if we set the same seed. So that's what's going to happen here. Now, how do we get a random walk out of this? This is not yet a random walk because we have to start adding these numbers together. So what we do is, it's called, if you've never seen this before, it's actually very simple. It's called writing loops. And a loop is very simply a piece of code that you repeat over and over and over again, hence the name loop. If you've done programming before, then you definitely know this, but if not, it's actually very simple. So let me show you how it works. Let's say I write x is equal to 0, and I run this. That means that if in the console window I type x down here in the window, I'm asking the computer to tell me the value of x, and will tell me the value of x is equal to 0. If I do x plus 1, it will give me 1 because the value of x has been set equal to 0. Now, if I type, so let me go back over here. If I was to type, actually, I'll do it in the console window again. If I type x is equal to 2, then that resets, then that changes the value of x. It eliminates the current stored value of x, which was 0, and now it treats x as 2. So I have reset the value of x, and now I make it be equal to 2. And now if I do x plus 1, then I will get 3, whereas before, as you can see, I was getting 1. So it's just what you set x to be. Now I'm going to do something that will look rather funny. So at the moment, x is equal to 2. If I write x is equal to x plus 2, mathematically, this is complete nonsense. That's an impossible equation. But the computer interprets this in a very different way from the way a person interprets this. You, as a person, you interpret this as an equation for x. The computer does not interpret this as an equation for x. The way the computer interprets this, it says, take x. Now, what is x? X is equal to 2, and add 2 to that number. So that means x plus 2 is 4. This quantity is equal to 4, and then you're telling it to take x and set it equal to 4. There's no error, and now if you check the value of x, it becomes 4. If you write x is equal to x plus 2, and now you check the value of x, it should be 6, because you took the current value of x, which is 4, you add 2 to it, that becomes 6, and now you're storing that answer in for the symbol for x, so it changes the previous symbol for x, and it makes it 6. Now, the reason why this is kind of funny is because if you write it the other way around, then the computer is confused, because the way it interprets the equal to symbol is differently. You kind of want to understand it is you're substituting that value in place of x. But because it's no longer a symbol by itself, but the symbol is paired with an operation, the computer gets confused, and that's why you get the error. So you just have to understand that for a computer, the equal to sign means something a little bit different. If you want to treat an equal sign like the way you're used to, so in this case, x is equal to 6. If you write double, if you use 2 equal signs, then you're doing a logical check. You're asking the computer, is this true? And then it says it's true. If you write x double equal to 5, then you're using the regular math equal to. This is a different equal to. This is more like equal to by definition. I think sometimes in computer science, in some programming languages, they do it like that. That's equal to by definition. But in R, in this software, you use that symbol to assign a particular value. Actually, another way you can assign it is you can assign it with an arrow. This is the other way you can assign it. This is another way you can do it. You assign 3 to x, and then you write x is assigned x plus 2. Then the new value of x becomes 5. So some people use this to assign. I like to just use an equal to symbol because it takes one less keystroke. And in math, we try to save as much time as we can. So with all of that explained, here's what I want to show you. So here's a problem. Find the sum of all integers, of all squared integers, from 1 squared to 20 squared. There is a formula for doing it, but we're just going to do it with a computer program. So here's the way you're going to do it. I'm going to set x is equal to 0. Okay? So that's my initial condition. How do I get the next number? So I'm going to write x is equal to, so I'm going to write x is equal to x, the previous value, which is 0, plus 1 squared. And that will give me 1. For the next one, I'm going to write x is equal to x. So this is the current value of x, which is 1. And then I'm going to go to the next number, which is 2 squared. And if I do that, and I click on x, then that would be 5, because it's 1 squared plus 2 squared. To get the next number, I would write x is equal to x plus 3 squared. And if I do this, that will give me 14. Okay? So that's basically the way it works. You keep on replacing x by x plus 1 squared, x plus 2 squared, x plus 3 squared, and you will do this all the way until you get to x plus 20 squared. But you see what the problem is. You do not actually want to write out 21 lines of code. That's kind of annoying. Imagine if the number was bigger, then we have to write out manually more lines of code. So here's the way we actually do this, and this is called a loop. We're basically doing the same exact procedure over and over and over again. We're just slightly altering the number that we're adding. So this is the way you would write it. It's just like sum notation. You write 4. You put square brackets, okay, 4, and inside, it's just like in summation notation, you have the index of summation. Let's say the index of summation is n, and you write n in, and then you're going to specify a list of numbers. It's very common in programming languages to specify a list of integers by using the colon. So 1:20 will specify numbers, this list of numbers from 1 to 20. If you type 20:50, that will just generate the list of numbers from 20 all the way up to 50. So here we're going to write 1 to 20, okay? And then we're going to use the set brackets. And inside the set brackets, you're going to write in what piece of the code do you want to repeat. Often the way people do it is they just jump to the next line. You do not have to do that. You can just keep it like this. This is perfectly fine. The point of these brackets is to indicate what piece of the code do you want to repeat 20 times. You want to repeat something 20 times. So what piece of the code do you want to repeat? So we're going to take x, and we're going to do x plus n squared. And now, if you highlight all of this, by the way, I forgot to say, but I think it should be self-understood. When you use this symbol, I'm not sure what this symbol is called, the pound symbol. So when you use the pound symbol, the point of the pound symbol is to allow human commentary. So if you want to write something for yourself, so the computer does not read it. Because if you remove it and you do this, you're going to get an error. It does not understand. But by putting the pound symbol, it completely skips over that, because that's just your own commentary for yourself. So you're going to select that part of the code, you're going to click run, and then you get to ask what the value of x is, and that would be the value of x. That would be the sum of all of the squares from 1 squared to 20 squared. Now there's a different way you can do it. There's an easier way you can do it. You can just write the numbers from 1 to 20. Then you can write the numbers from 1 to 20 parentheses squared, and that will just square all of the numbers in the list. And then you can probably guess, you can tell it to sum all of the numbers in that list, and as you can see, it gives you the same number. But so there is an easier way to do that. I mean, this is by far the easier way to do this. But of course, we're specifically trying to illustrate how loops work, so that's why I'm writing it like this. So I imagine that probably for many of you, you've seen this before, but if not, that's the way loops work. Let me clear the console window by clicking on the broomstick. And in fact, there's another button over here. You see this button? This button means minimize. So if you click on the minimize button, it will bring it down so you have more writing space in this window. So here is how we are going to create our random walk. So I'm going to write W for the random walk. I'm going to initially set the random walk to be equal to 0. Now, I want my random walk to include all of the previous numbers as well. So the idea is, so I'm going to bring up the console window, and it just depends which one you click. If you click on the large square, it shows you the whole thing. So if I said W is equal to 0, so W is now 0. This is the way the random walk starts. And I want to be able to add one, or I want to add 1, or I want to subtract 1 from W, and I want to do it randomly. But I want to do it in the way so I keep track of all of the previous number. That's going to be useful to visualize what's happening. So we're going to use a feature called C. As I've mentioned before, this means combine. So if I write 2, 3, that combines the numbers 2 and 3 into a list. If I write 3, 2, that binds 3 and 2 into a list. You can even repeat, that's fine. Okay. So if W is currently equal to 0, and I write combine W with W, what would that be? That would be 0, 0. And if I write combine W with W, well, now, okay, so that would be 0, 0. But now let's say I said W is WW. So that would be 0, 0. So now the new value of W, it's no longer one number. It's now a list of two numbers. And if I write W is WW, you can think about what that would be. That would actually be, so W is two numbers 0, 0. W is now two numbers 0, 0. So this is now a list of four numbers. All of them are 0. Okay, so that's what that would be. If I write W is equal to combine W with the number 1, then that would be four zeros followed with a 1. If I write W is W comma negative 1, then that would be 1 and negative 1. And that's the idea, that as I do this, that will allow me to generate a sequence, because the idea is that you want to keep on adding 1 and negative 1 to every other number that follows. So here's the way we're going to do it. We're going to set W is equal to 0, and then we're going to replace W by what it currently is, and then we're either going to add 1 or negative 1 randomly. Let's say we make 1, and then this becomes W. And then we take W, and we write combine W, and this time we write negative 1. Then our sequence goes, actually, sorry about that. That's I did not, let me try doing that again. W is 0. W is, it's the current value of W. Okay, so I guess I should have said this before. So I should explain this. I did not explain this. Let's say W is the numbers 1, 3, 5. If I write W at 1, that's going to extract the first number in the sequence. W at 2 would be the second number in the sequence, and W at 3 would be the third number of the sequence. If I do W at 4, I get not available. So it's convenient that instead of giving you an error, it gives you a symbolic to just tell you that it's not there. So here's what I want to do. So here's how we're going to generate a random walk. We're going to set W is equal to 0, and then we're going to write W is, it's the current value of W. So it's going to be W1, which is at the moment 0. I'm sorry, it's going to be W, and then W of 1 plus, and now you're going to do it randomly. You're going to either add 1 or subtract 1. Let's say I add 1. If you look at what W is, it's 0, and then we added 1 to the previous number. And now I'm going to kind of repeat the same thing. By the way, this is very convenient. If you look at your keyboard, you have the arrow keys. If you hit the up key, it returns the previous code that you executed. If you press the up key again, it goes 2 lines back. Okay, so this is very convenient. So you do not have to copy and paste. You can just click on your arrow keys. So this is what we have. And this time, instead of using 1, I'm going to use I have 1 and I have 2. I'm going to use this previous number, which is now in position 2, and I'm going to add to it 1 or negative 1. So let's say I add 1 to that number. Then look what happens to W. It was 0, it's 1, it's 2. So that means that this is my random walk. And I'm going to repeat the same thing again. This time I do W3. Let's say I keep it as +1. And now if you look at what W is, it's 0, 1, and 2. And you can see this is creating for you a random walk where you just keep on adding the number 1. And now we're going to add randomization to how you add plus or minus 1. So here's the way you actually code this on the computer. So let's open up the script window. I'm going to click on this button over here to maximize it. So I'm going to keep the seed as 807 so we can get the same exact answer. I'm going to set W is equal to 0. And here's where I'm going to write the loop. I'm going to write for, and how long do you want to do this? So let's say we want to do this for 1,000 steps. So I'm going to write for n is equal to, and this part might confuse you. You would think I'm going to do it from 1 to 1,000, but actually I'm going to do it from 2 to 1,000. The reason for this is because in mathematics, we often begin our indexing counting starting at the integer 0, whereas in our software, you start the index always at 1, not at 0. It depends on the software. I think in Python you start at 0, not at 1. But the way you do it in our software, you start always at the number 1. So technically, this is starting at 1. So it's a little bit annoying. It kind of shifts everything off. And here you're going to write your loop block. This is what you're going to say. You're going to say W is equal to, this is the random walk, is equal to, you're going to combine the previous one, which is n minus 1. I'm sorry about that. You're going to take the current block of numbers. You're going to look at the previous one, and you're going to add a random number, either plus or minus 1. This is the way you write it. You're going to sample negative 1 and 1, size is equal to 1. You're just going to add one number to whatever that number is. And let's execute all of that. And now, if I click W, it will be a very long, messy list of 1,000 numbers. So it's convenient to just write head W. That's just going to show you the beginning part of the sequence. So this is your random walk. It moved down, 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 up, up. And if I do tail of W, that's going to give me the end of the sequence. And look at that. It's actually kind of, numbers got fairly large. It moved up, 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 up. Okay? And here's another thing you can do, is you can tell it to plot the sequence. So we'll just plot the sequence like we did, where the horizontal axis represents time, and the vertical axis just represents the value of W. And if you plot that, you would actually see the plot right over here. It's a bunch of circles, but because you have 1,000 circles, it creates this solid curve. If you make the number a little bit smaller, so let me do this. Let's go back to this code again, and instead of using 1,000 numbers, let's use 50 numbers. Make the numbers a lot smaller. And let's just, and at the end, I'm going to write plot W. Okay, so I'm going to make it only be 50 numbers. If I do that, then you actually get to see the dots, right? So those are the dots, that's how they move. But I decided to make it be a bit more interesting and to use 1,000. So when I do that, this is your random walk. So you've generated 1,000 coin flips. And this is what happens when you randomly add 1 and -1 as you play the game. And this is actually quite interesting. Look at this. You consistently stay negative. Even though this is a fair game, that's kind of strange. Even though this is a fair game, you stay negative for the duration of the entire game. If you're wondering how that can be, how can you stay negative for the whole game if it's a fair game? Well, the thing is, if you were to go out further, you see, we're only going up to 1,000. Let's say we were to go up to 10,000. Its behavior is very complex. So if you were to make this 10,000, it would probably, no, look at that, it still keeps on going down. Let's make it be 10,000. Let's make it be 100,000. You see this button that says stop. You can feel the computer being a little bit slow. Okay, so here's the plot. You can kind of see it's starting to go up again. And that's the whole point, that if you were to wait sufficiently long, even though it appears to be always negative, it will eventually come back positive. We're going to prove that. It will come back, it has to come back positive. And by the way, let me make it 1,000 again. And let me do this. So let's execute the code. So this is what we had before. And I'm going to do this. I'm going to select everything, but not set seed. And the point of this, I'm doing a random experiment again with the next block from the random number generator, not beginning with the initial condition, but further out in the random number generator. And then it goes like that. And if I do it again, and now you can see the behavior is different. It was negative, then it became positive, then it became negative. And as you keep on clicking run, you can see the behavior is quite different. Here it kind of more like that. And sometimes it becomes positive. This one goes positive. So you can see its behavior is very complicated. That even though individually the coin flips are easy to understand, the behavior of this thing is quite complicated, as you can see. I also want to show you what happens when it's an unfair coin. If it is an unfair coin, then the way you would modify this is at the moment it's selecting 1 and -1 with 50% probability, but you would write probability is equal to, and then you would put a combined vector. This is a vector, or a list if you prefer, that gives you the probabilities for these two numbers. So let's say we make one number 45% and we make the other one 55%. Okay, so this is what you would write it. So this one is 45%, this one is 55%, and now if you execute this, you can actually see it starts to go up. That makes sense. And if I select everything again, skipping the initial condition, you can see now it's always positive, which makes sense because it's more favored to go up. It's more predictable now, right? When the random walk is symmetric, when it's equally likely to go up and down, that's the most interesting case. That's the one that's the most chaotic one. This one's more predictable. The more favored you make it be on heads, the less predictable, the more predictable it becomes. If this is 75% and that's 25%, then just to show you, that's almost a straight line. It's not actually a straight line, but it's close to being a straight line because it becomes less and less unpredictable. So that's, you can still see some small bends in the curve, but it's not that interesting. heavily favored to be heads. So the most interesting case is, of course, when it's symmetric. And that's where things get a lot more interesting. It gets very wild and chaotic. And trying to understand the behavior of this is what the study of random walks is all about. Okay, so that's the way you can simulate random walks on a computer. You can see them and you can play around with this yourself. It's fairly interesting. But the question, of course, here is, how do we justify the existence of such a sequence? How do we know that such a sequence exists? So we're now going to discuss something that's fairly theoretical. We have the theory to do this, and I want to talk about that next. I want to justify the existence of such a sequence. Now, if you're not interested in that part, you can just skip. I have no idea, maybe 20 minutes or 30 minutes, however long it takes. Just skip that part if that does not interest you. But I do think the theory is still interesting. It's nice to see how the previous probability theory that we've talked about connects nicely to what we're doing right now. So now we're going to discuss the justification for why this sequence of independent random variables exists that has the desired properties. Now we're going to state a theorem. And this is a general theorem. We're not going to prove the general theorem because that takes more work, and rather we'll prove the special case of this theorem that we're using. And the theorem says that if we have a sequence Pn is a sequence of probability measures on the real line with the Borel algebra, then there exists a probability space together with a sequence of random variables where each one is a random variable from the sample space to the real line, so that this sequence is independent collection of random variables. So all of the random variables that make up the sequence are independent with respect to one another, and their distributions, so the distribution of, so the push forward, so this is the fancy way to say it, xn star of p is equal to Pn. In other words, the distribution of xn is precisely Pn. Basically, what the theorem says is that if you assign distributions, if you assign probability measures, then you can construct a sequence of random variables defined on the same sample space in an independent way, so that every single one of these random variables, their distribution, so the distribution is the probability distribution you get on the real line. So in fancy language, it's the push forward of p, which is the probability measure on your sample space, matches the prescribed distribution, the probability measure you gave at the very beginning. So that's the theorem. And then there's an immediate corollary of this theorem, and this is what we're doing. That now, in the statement of this theorem, we're not assuming that these are discrete probability measures or anything like that, but you can make these all be the same. So you can just make this be the discrete distribution that's the equal sum of these two Dirac point masses at -1 and 1. So you make every Pn be the same. And then there exists a collection of random variables so that each of these are discrete and their distribution is exactly that. And that is exactly what a collection of independent coin flips is. It's a sequence of random variables that has such a distribution. But we're going to prove not the general theorem, but the special case where it behaves in this way. And the proof of the general theorem is actually just like the proof of this special case, but it takes a bit more work. You have to do something more with it. So here's how we do it. We're going to construct. So first, it would be helpful, we're going to construct a sequence. Let's call it yn, where each, so this is an independent sequence of random variables, and the distribution of, so this is another way we write distribution. So the probability distribution of each of these is, so instead of being a half delta negative 1, it would be this. So basically it's just like what we had before, but these random variables, instead of producing 1 and negative 1, they rather produce a binary sequence filled with 1s and 0s, where you think of 1 as representing heads and 0 as representing tails. So then if we set xn, so if we rescale y by 2 and we shift, then the probability, then the distribution of this random variable will get shifted appropriately, because if yn is equal to 1, then this is 2 times 1 minus 1, so that would be 1. And if yn is equal to 0, then this would be 2 times 0 minus 1, so that would be the other value. And then this collection has the desired property, namely that it's independent, though you do have to check that it's independent, but that's not really that surprising because xn is just a rescaled version of yn, and since these y's are independent of each other, it will mean that the x's are independent of each other, though that does take a little bit of a check. And it has the desired property that the distribution of each of these xn's is exactly what we want it to be. So therefore, the question comes down to how do you construct such a sequence of random variables? Well, the idea is that this is supposed to represent coin flipping, an infinite sequence of coin flipping. So here's what we do. I'm going to remove all of this, and I'll start from the very beginning. So let omega be the set of all binary sequences. So you would just say this is the set, and you have a sequence of numbers with the property that an is equal to 0 or 1 for all n. And this is actually a very large set. This set is uncountable, and it has the same cardinality as the real line. You're going to see why that is later on. You can show it's uncountable by using the famous Cantor diagonal argument, if you are familiar with this. If you have a binary sequence, if you go down the diagonal, if you have a sequence of binary sequences, you go down the diagonal and you invert the zeros to the ones, and then you constructed a new sequence which is not in the sequence that you have. Hence, it's not possible to enumerate all such sequences. So that's the way you would justify it's uncountable. But just because it's uncountable does not automatically mean it has the same cardinality as the real numbers. So you're going to see very soon why it has the same cardinality as the real numbers. This does not actually matter, by the way. If you do not know what this means, if you do not know what it means to be uncountable or what it means to be cardinality with the reals, ignore that. That is completely irrelevant. I'm just trying to say this is a very large sample space. It's clearly not finite, but it's not even countable. Countable just means it's not possible to list all of those in a sequence. You might be a little bit confused because the elements of the sample space happen to be sequences, but I'm saying the collection of all such sequences cannot be listed into a larger sequence that contains all such sequences. If you're confused by what I said, ignore that. It completely does not matter for what we're doing. It's just an interesting observation. So this is a very large sample space. And okay, and then we're going to define functions xn from the, actually I'm going to call these yn, because this is going to be my modified sequence of random variables that will give 0 or 1. And this will map the sample space to the real line. And what does it do? It takes a sequence. Maybe I should not call it n over here. That confuses the notation. I'll write it like this: I bigger than or equal to 1. And it extracts the nth number in that sequence. So quite simply, this is just a projection onto the nth coordinate. So that's what yn is doing. Yn is projecting. It takes the sequence, it looks at the nth coordinate, and it extracts out the nth coordinate, and that number will either be 0 or 1. Okay? So each yn has only two outputs, 0 or 1. So this is going to indicate that you have a discrete random variable. It has two outputs. And then we want the probability of y taking on those two outputs to be equally likely. Now we want the probability that yn is equal to 0 to be 1/2, and the probability that yn is equal to 1 to also be 1/2. We're basically trying to say we want this to be a fair coin flip, that the probability that the nth outcome on the sequence ends up being either heads or tails happens with equal chances. Now, you probably know that we have a problem. And the problem is, at this moment, we've only defined the sample space. In order to define the probability space, we need to say what the sigma algebra is, and we also need to say what the probability measure needs to be. So this, at the moment, does not make sense. But this is the motivation for how we define everything. So this one, well, let's just write this out. So note that the set, now this is of course a shorthand notation for saying sample points in the sample space, and we need to understand that a sample point itself is a binary sequence, but for notational simplicity I just denoted by lowercase omega, but this omega should be understood as an infinite binary sequence. We want that its nth position to be 0. So we want that the nth position in that sequence to be equal to 0. That's what that is. Okay, so let's give, okay, and then the other one is where wn is equal to 1. Now, how does this look like? Well, the way this looks like is, as a set, this is going to be, so the first coordinate, so as a set, it's a set of sequences that's going to go like this. So the nth coordinate, so the nth position has to be 0. And in this one, this would be the same thing. It'll be an infinite binary sequence, but here the nth position is going to be 1. But all of the other ones, they could be anything whatsoever. And we want these to be events, because if this is a random variable, then it has to pull back the singleton set into an event. So this has to be an event, so it has to be contained in your sigma algebra. So let me give this one a name. So this entire event, so this is an event. This is the collection of all binary sequences whose nth position is equal to 1. It does not care about the other positions. So these ones do not matter. This could either be 0 or 1, 0, 1, 0, 1. The only requirement is that the nth position is equal to 1. So let's give such an event a name. So we're going to call this event E subscript n. And this event would then just be the complement. So this one will just be omega take away En. So I'm calling this one En because I think of 1 as heads and 0 as tails. So this is the event where the nth outcome was heads, disregarding all of the other outcomes in that infinite sequence of tosses. Okay, so now the idea is this. We want, for these events, En, to be in this sigma algebra. Because otherwise we do not have a random variable. So the ENs have to be in the sigma algebra. Now, and what else do we have? Well, and then we have intersections. So let EN intersect EM be denoted by, more simply, EN comma M. Let's say for N not equal to M. Otherwise, I mean, they could be the same, but then it's just the same event. So what is this supposed to represent? This is supposed to represent the event that you got heads on top. So to use an example, if you have E2 intersect E4, this is supposed to represent the event of infinite coin tosses where on the second outcome you got heads, and on the fourth outcome you got heads. And on the remaining outcomes, the remaining positions, it does not matter. That's what the event is supposed to represent. And more generally, we can also talk about so EI1 intersect EI2 intersect EIN. So if you have a bunch of indices, it would be convenient to just denote that at EI1, EIN, like this. And because the order does not matter, whether you write EN and EM, or EM and EN, we also can assume that they're different, so you can just assume they're written in ascending order. Okay, so more generally, let I be a multi-index. So what is a multi-index? In other words, I has the form, it's a collection of positive integers where the integers were the consisting of a strictly increasing sequence of positive integers. And we want that every, and let me just add this, and we denote E subscript I to just be the intersection of all of those events from before that we've mentioned. So this is just done for notational simplicity. We want that our sigma algebra that we're trying to construct, it should contain every E subscript I for all multi-indices I. So what we're going to do is that, so we will define the sigma algebra for this sample space to just be the sigma algebra generated by all of these EIs. So let's just explain what happened. Basically, we made the observation that if we want yn to be a random variable, we better have it that this one and this one belong to the sigma algebra. Now that's just a complement, so let's just focus on the ENs. Now anytime you have a sigma algebra, it has the property that the intersection of any two events has to be an event. Now as you keep on intersecting these, you get these types of events, and we gave them a notation. We used multi-index notation where you pick a strictly increasing sequence, a strictly increasing finite sequence of positive integers, and then you denote E subscript I to be the intersection of all of those. And if these are events and you have a sigma algebra, which you're supposed to have if you have a probability space, then whatever this is has to belong to your sigma algebra. And then we define the sigma algebra as the smallest sigma algebra out of all of the sigma algebras. You just take the smallest one that happens to contain those events. Now, the reason why the sigma algebra can become quite complicated is you need to understand that if you start taking the various types of EIs and you start forming unions of them, especially countable unions of them, you can generate some fairly complicated events. So that's what the sigma algebra is. Now, the next question that comes up is we have, so at the moment, we defined a sample space with a sigma algebra, okay, and measurable functions from the sample space to the real line so that every one of these is equal to 0 or 1. What do we mean by measurable? By measurable, we just mean they're random variables, that if you take something in here and you pull it back, it's going to be an event. And the reason is very simple, because every one of these YNs, they're projection functions. They only have two possible outputs, only two possible outputs. So you just have to pull back those two possible outputs and see if they end up in the sigma algebra, which they have to, because that's kind of the reason for why we've done them, right? The whole motivation for doing that is that these are, we want these to be random variables. We want them to be measurable. So when you pull these back, they have to give you something in the sigma algebra. So by construction, they're going to be measurable. So what we're missing, what we are missing is a probability measure on this pair. How to define such a P, such a probability measure. So this is where we're going to construct P based on what it wanted to do. Okay, so we want that the probability that Yn is equal to 0 should be 1/2, and that the probability that Yn is equal to 1 should also be 1/2. So then how do we do that? Well, but you have to recall what this is. This is just another way of saying this is the event that we're calling En, and this is the complement of that. That would be sigma take away En. So then how do we do that? So this force, so we are forced to conclude that the probability of this event En has to be 1/2. Okay, and now this is where we're going to use independence. And since we want independent coin flips, it means that more generally, that the probability of E subscript, that multi-index, should be equal to 1/2 to the n if the length of the multi-index is equal to n. Okay, so the length is just how many integers you have in the multi-index. If you're confused by that, let me just show you a very simple example. What would be the probability of E1, 3? Okay, that's your multi-index. Well, what is that supposed to represent? That's E1 intersect E3. And we want the outcome, so we're basically saying what's the probability of getting heads on the first outcome and heads on the third outcome? Well, if the two tosses are independent of each other, it should be 1/2 times 1/2, right? That's what independence means. And independence means multiply. Multiply is independence. So this should therefore be to summarize, let's say what we have. The sample space, this is the set of all binary sequences. And we're going to make our sequence index begin at 1 here. The event, I'm sorry, the sample space. And before I get to the sample space, I should say this. So if I is a multi-index in the positive integers, let's also say an increasing multi-index. All that means is that this is a finite sequence of positive integers that are increasing, a multi-index. So if I is a multi-index in the positive integers, we define E subscript I to be the intersection of EI1 intersect EI2 intersect EIK, where, well, I'm not going to write out what this means. So this is what we've defined before. So this is just a collection of sequences where the I sub 1 component is equal to 1. So that's where you have heads on the I sub 1 toss. And the sigma algebra, this is the sigma algebra generated by all of these events of this form. So then we claim there exists a probability measure P on this pair, the sample space with this sigma algebra, so that the probability applied to this event is then equal to 1 over 2, and by the absolute value of I, we just mean the length of this multi-index. If you do not like that notation, maybe you can do it with 2 bars. It's just the length of the multi-index. Of course, if this is the empty multi-index, then the empty intersection is understood to be the empty set. So that is what we have here. Now, how do we know that such a probability measure exists? How do we justify that there is such a P, such a probability measure? So let's just accept this for now. Normally, the way we would justify this is by using the Carey-Theodori extension theorem, but there is a more elegant way to do it that will make it easier. So let's just accept it for now. So assuming that P exists, then the map that takes the sample space to the real line by the property that yn of a binary sequence is just equal to the projection to the nth component, is a random variable. And the reason we explained why that was basically by construction, because when you pull back an event, there's only 2 possible outcomes, and we've constructed these events in such a way so they are forced to belong to the sigma algebra. So this is a random variable, and this collection, this sequence of random variables, forms an independent sequence of random variables. This is, again, by construction, because for these to form an independent sequence, this is the reason for why we've defined the probability of this event to be this. We do it by multiplying across the intersection. And then finally, and each yn has distribution 1/2 delta 0 plus 1/2 delta 1. That it only has 2 possible outcomes, 0 and 1, and they're equally likely to happen. So everything has been justified. What remains is to show that this P, that there exists such a probability measure. So the proof here is actually very interesting, the way you can justify that. Without using the Carey-Theodori extension theorem, we're going to do it a little bit differently. And it's based on this idea of expanding a real number in the interval from 0 to 1 into binary. So here's how you do it. It's a very simple idea. So here's the interval from 0 to 1. And somewhere in the interval, you have a real number. Okay, so we have a real number. Let's call that number x. So here's the way you expand it into binary. It basically means that you want to write x in the following form: a1 over 2 to the 1 plus a2 over 2 squared plus a3 over 2 cubed plus a4 over 2 to the 4th. So you're forming this sequence, and the digits, and each ai is equal to 0 or 1. That's what you call binary expansion of a real number. It's very similar to how you expand a real number into decimals. When you're using decimals, you're using powers of 10, but here you're using powers of 2. And the easiest way to explain it to you is by just drawing some pictures. Of course, you can work out the formal details of this, but it's not too difficult. Basically, the way you do it is you cut it in half. You cut the interval in half, and then you ask, are you located on the left or are you located on the right? If you're located on the left, you use 0 as the digit, and if you're located on the right, then you use 1 as the digit. So in this case, we get 1. So this is going to be 1 in this particular example. And then you take this subinterval and you cut it in half again. Right? So you kind of eliminate this one. Now you have two halves, the left half and the right half. We're in the left half, so this one is going to be 0. Then we remove the other one. We focus on the subinterval that we have. We cut it in half. And you can see we're located on the right side, so that's going to be 1. And we just remove the one we missed. Then we cut it in half. Are we on the left or right? We're on the left, so that's going to be 0. This one gets removed. And then you can see it's on the right, and so on. So this is an infinite process, and it will generate for you a sequence of 1 and 0s. And if you were to form this infinite series, that infinite series will converge, right, because it's dominated by a geometric series, and it will converge exactly to that number x. That's not difficult to prove. The one thing I want to say about this is if your number appears as a midpoint as you cut it in half, then you can do it in 2 different ways, and both answers would be correct. So let me show you what I mean. Let's say this is 1/2 and this is 1/4. So how would you write 1/4 in a binary sequence? So you cut it in half, and you can see that you're on the left side. So the sequence will start off as 0 over 2 to the 1 plus, and then you cut it in half, and then you remove this piece, and you're left with the left side, and you cut it in half. And now it's a little bit ambiguous because 1/4 is both in the left subinterval and in the right subinterval. Which one do you want to use? Let's say you use the one on the left. So if you're using the one on the left, I'm sorry, let's use the one on the right. If you're using the one on the right, then you will have 1 over 2 squared. And then you will remove this subinterval, and now if you cut it in half, you're on the left. You cut it in half, you're on the left, and you will keep on staying on the left. And so you will generate the following infinite series. But you can see that everything's 0 except 1 over 2 squared, which is 1/4, so that works out. But there's another way you can do it that might look funny, but it leads to the same answer. That we're going back, this is 1/2 and this is 1/4. The other way you can do it is you can, so the first one is forced on you. You're on the left half. So that's going to be 0 over 1 squared plus. Then when you cut it in half, because 1/4 is in both subintervals, you get to choose which one you want to use. Let's say this time you choose the one on the left. So then you would have 0 over 2 squared. It looks wrong, but you will see it actually works out. So you remove the one that you did not use, and then you cut this one in half. So when you cut it in half, you get to see that 1/4 is on the right. And when you cut it in half, you get to see the 1/4 is on the right. So it will always be on the right. So then you can also write it as 1 over 2 cubed plus 1 over 2 to the 4th plus 1 over 2 to the 5th, and so on. And it looks like this is incorrect. This actually works out because this is a geometric series that sums up exactly to be 1/4. So if it appears as a midpoint in one of these bisecting intervals, then there's actually 2 ways how to do it. But in most cases, such a representation will be unique, and that's what we call expanding a number into binary. Okay, so here is what we're going to do. This is a very, very interesting idea. So there is a map. So we have a map. I'm not even sure if we should give this map a name, but let's call this map F. So there's a map that takes us from binary sequences. Okay, let me do it like this. So there's a map that takes you from binary sequences into the interval from 0 to 1 by doing that process. The map is not necessarily injective because, as we saw, it could happen that you can have two different binary sequences that represent the same number, but the point is it will always end up somewhere in 0 to 1. It's very close to being injective, though. By the way, this is why this set is uncountable, because this mapping is almost a bijection. You have to clean it up a little bit, but it's almost a bijection. And then there's a map from the interval from 0 to 1 to the unit circle. And this is what we call the exponential map. Okay, so this is the map that takes a real number. Let's call this real number x. And it maps it using Euler's identity, e to the 2 pi I x. And then by Euler's identity, that's cosine x plus sine plus, well, it would be, as we all know, that's cosine 2 pi plus I sine 2 pi. So that's a complex number of norm 1. So this is the map that we're going to use. So this is an exponential map where you multiply by 2 pi because you want it to be on the unit circle. So let's call this composition that takes us from binary sequences directly to the unit circle by f, for lack of a better name. So we have this map. And now you're going to observe something quite interesting. So we observe that the event, that EI, gets mapped to a union of arcs of S1. So allow me to illustrate this in a very simple example. So the easiest one to look at is where the multi-index consists of just a single integer. Let's say it's E subscript 1. That's the smallest integer, and this is a multi-index of length 1. So this is going to be binary sequences that have a 1 in the first position, and they could be anything else in any other position. So it's the set of binary sequences that look like this. Okay, so the 1 does not mean, so it's a little bit confusing because the 1 does not mean that you have a 1. The 1 just indicates the position in where you're at. So maybe I should use a different color to make that clear. So this just indicates that you are in the first position. So you have heads in the first toss. The remaining entries do not matter. Now, where does this get mapped on our unit circle? This is our unit circle. So think about this. We're doing this in two stages. We're first mapping this to the real line, and then we're mapping the real line to the unit circle by using the exponential map. So if the first position is 1, then that means the set of all such binary sequences means that when you write it in binary, all of the numbers are in the second half. So this will get mapped to this second half. And then this piece under the exponential map gets wrapped around the circle. So 0 goes here, the midpoint goes there, and it gets wrapped around like this. Okay? It gets wrapped around like that. Now look at this. We have a probability measure, and I'm going to call it Q, on the unit circle. Technically, it's the unit circle with the algebra generated by all of the arcs, but I'm going to be a little bit sloppy. So we have a probability measure on the unit circle, so that if A is a subset of the circle is an arc, then the probability measure of that arc is equal to, it's the length of the arc divided by 2 pi. So we actually talked about this example in a lot of detail all the way in, I would say, lecture number 2, I think. That was our first serious lecture. And observe that if you were to map this event, so F is the mapping that takes this event onto the unit circle, and then you apply the probability measure from unit circle to that event, then that will give you 1/2. You see that? It gives you exactly 1/2, because you can see it takes up half the length on the unit circle. Now, to show you another example, let's say we had E, and the multi-index was, to keep it simple, 1, 2. Then this would be the set of binary sequences where you have a 1 in the first 2 positions, and then everything else is whatever you want it to be. So this will just mean it's in the first position and it's in the second position. And when you map that to the interval from 0 to 1 in binary expansion, where do you end up? Well, first of all, you end up in this half, right? You end up in this half, and then you end up in the half of that half. So you will actually end up right over here. And then you can see when you map it to the unit circle, you would be right there. And so what we see from here is, so if you apply the probability measure that's on the unit circle, and we do F of E subscript 1, 2, that would give us 1/4. You see, it's giving to us what we want, right? Q applied to that gives us what we want. Okay, what else do we have? So the other thing that we have is, let's say we have E, to do another example for you, E subscript, let's say it's 2, then that would be the set of binary sequences where you have a 1 in the second position. So the 1, you have heads in the second position. And visualized on the real line, those will be numbers whose binary expansion, so this one's a little bit tricky. You cut it in half, and then you cut it in half. Okay, so here's what's going to happen is we're going to cut it in half. So the first one, we do not really care about the first one. It's just that the second number has to be a half. So we cut it in half again, like this. And this is the way it's going to look like, right? Because the 1 means that on the second bisection, you're on the second side. You're on the right side. But when you map that to the unit circle, what does that give us? That gives us that where, so this is 1/2. So this is going to go like this. So this is where this event will go. So it's a union of 2 disjoint arcs. Each of the 2 arcs is 1/4, but together their length is 1/2. Well, their length divided by 2 pi is 1/2. And so Q applied to FE2 would be equal to 1/2. Okay? And in general, so hopefully these examples convince you. I know this is not a full proof, but I think it's pretty convincing that in general, if you take Q, this is the probability measure on the unit circle. So basically, you're taking an event among binary sequences, and then you map it to the unit circle, and then you apply the probability measure on the unit circle. This will be equal to 1/2 to the length of that multi-index. So that's the one that's going to matter. It's just the length of the multi-index. Okay? And so So we can use, so we can define, we can construct a probability measure P on this sample space with that sigma algebra as follows. Here's what you would do. You would say that if E is an event in general in the sigma algebra, then the probability of this event is then defined in the following way. You would map that event to the unit circle, and then you will apply the probability measure on the unit circle. The fact that this is a probability measure follows from the fact that Q is already a probability measure on the unit circle. And it has the property that if E is of the form, it's of the special form, then the probability of this special type of event will just be determined by the length of the multi-index. The reason for this just follows from what we said over here. So we're circumventing the need to justify the Carey-Theodori extension theorem by simply taking advantage of the fact that we can map these events to events on the unit circle and then use a probability measure that we already have from before as a way to help us construct a probability measure on this space. In a way, if you think about it, what we're doing is we're doing a pullback operation. Remember we talked about how if you have a random variable that induces a new probability measure on the real line by a push forward? This is somewhat similar, but this is like a pull back. You're taking a probability measure on one space and then you're pulling it back to this space to construct a new probability measure. But from here, we get exactly what we want. And this justifies the existence of such a sequence. Okay, so in the end, now you do not actually have to go through this process. Generally, what we do in probability theory, and this is the two summarized version, we're saying is that there exists a sequence yn, each yn, an independent sequence of random variables, and each yn is discrete with the probability that yn is 0 is a half, and the probability that yn is 1 is also 1/2. So every one of these two random variables has only two values, 0 or 1, heads and tails. And now if we set xn to be equal to 2yn minus 1, then the sequence is an independent sequence of random variables, and the probability that xn is equal to plus or minus 1 happens with equal probabilities. And this is the starting point in how we construct a random walk. So often we never go back to the sample space and we just use the properties of the random variable. And with this, we can then define a random walk to just be the sum of these. That's the way we can go ahead and define that. I do want to just give a small little disclaimer. There's some people, instead define a random walk as this entire sequence beginning at 0. So the convention is that w at 0 is just a constant random variable which is equal to 0. So it's just a matter of how you choose to define things, because some people want to think of a random walk as something that evolves over time, whereas this is just a snapshot at one particular moment in time. So do you define this random variable as your random walk, or do you define the entire sequence as your random walk? So it's just a matter of convention and how you choose to do that. So now that we have mathematically justified the existence of a random walk, okay, the next thing I want to talk about is I want to discuss the properties of a random walk, mathematical properties of a random walk. For simplicity, let's say we take the random walk up to time 4. And we're going to ask the following question. What possible values can this random variable take? This is a random walk up to time 4 steps. So by definition, this is x1 plus x2 up to x4. And every single one of these gives you a random number, plus minus 1. And they give you a number independently of each other number. So one number that you can have is when they're all positive 1. So then you would have 4. So you have 4 positives. You can have 3 positives and 1 negative. So if this is 1, 1, 1, negative 1, well then the 1 and the negative 1 cancel, and that gives you 2. You can have 2 positives and 2 negatives, and then they cancel, and you'll get 0. And then you have the same thing in the negative direction. So these are the possible values that W4 can take. What about W5? Well, they can all be positive 1, so then you can have 5. We can have 4 positives and 1 negative. That would be 3. And then we have 1, negative 1, negative 3, negative 5. So in general, the random walk up to time n can be equal to any integer where the integer is between n and negative n, and you also want the integer to be even or odd depending on whether your random walk time is even or odd. So what I mean is, here we're talking about time 5, and so the integers are all odd. Here we're talking about time 4, and so all of the integers between 4 and negative 4 are even. And the way you would write this mathematically is you would just say that I is congruent to n mod 2. So that's the way you would write that. Now the next question that we're going to ask is, with what probabilities does Wn equal these integers? More specifically, what we're asking is, what is the probability that Wn is equal to one of these integers? Because Wn, after all, this is a random variable. The position of the random walk at time n is random. But we do know, whatever the position is, it has to be an integer between those two bounds satisfying this condition. And now we're asking, with what probability does it take on that integer? So to make this easier to understand, let's just return to W4, and then you'll see how it works in general. let's say we were to ask, what is the probability that W4 is equal to 3? Well, that one's kind of clear. That's going to be 0. Because as we remarked, the random walk up to time n will have to give you an integer between negative n, and it has to be either even or odd, depending on whether the time is even or odd. But let's say we take 2. Well, let's start easier. Let's start with 4. Now, what is the random walk? So the random walk is, by definition, the sum of these random variables. They're all independent of each other. And by definition, their sum is equal to W4. And we want the sum to add up to 4. Now, because every single one of these numbers is either plus or minus 1, and there's 4 of them, the only way you can add up to 4 is if all 4 of them are equal to 1. So you would just say that this is the probability that x1 is 1, intersect x2 is 1, intersect x3 is 1, intersect x4 is 1. And this is just a shorthand notation to say this is the set of sample points in the sample space. And keep in mind, the sample space, we try never to reference the sample space because it's fairly complicated, but the sample space would be the collection of binary sequences where the first component is equal to 1. So that would just be 1, and the remaining ones could be anything, where omega is this. And if you recall in our notation, this is the event that we call E1. This is the set of sample points whose first coordinate is equal to 1. So this is going to be E1. This is E2, E3, E4. And so this is the probability of E1, 2, 3, 4. It's the intersection of all those 4. And how was the probability measure defined on such an event? It's given by multiplication because of independence. We want to be able to say that these happen independently of each other. So the probability measure was defined to be 1 over 2 to the 4. So that's what it would be. So that's what you would do if you write it out very, very, very carefully. But generally, we write it out in a sloppier way. I mean, this is correct, but it's, as far as notation is concerned, we would normally write it like this. We would just say x1 has to be 1, x2 has to be 1, x3 has to be 1, and x4 has to be 1. The comma can be interpreted as an intersection. This is an intersection. And by independence, you would multiply it across. Because basically, this is essentially the joint distribution of those 4. And independence means the joint distribution is the product. It's the product of the probability distributions. It would be this. So this is usually the way you write it. And these are coin flips, and every single one of these is a half. And that's how you get 1 over 2 to the 4. Now let's do something that's a little bit harder. Let's say this is 2. So how can you add up to 2? Well, if you think about it, it would mean that 3 have to be plus 1, and 1 has to be negative 1. So you could have 3, 1, 1, 1, 1, negative 1, 1, 1, negative 1, 1, 1, negative 1, 1, and then negative 1, 1, 1. So that's what that would be. So now individually, the probability of getting this particular sequence, 1, 1, 1, negative 1, that would be 1 over 2 to the 4, like what we have before. But there's 4 different ways you can write that, so that would really be 4. Because it's a sum, right? It would be, like, if you carefully write it out, it would be the union of these 4 intersections. So if you're not sure what I mean by that, so here's what I mean by that. This would be E1 intersect E2, intersect E3, intersect the complement of E4. So this would refer to that one. But that's just one way, and then you have union, and you have E1 intersect E2, intersect omega minus E3 intersect E4, union. As you can see, the notation is pretty horrendous, but these are disjoint events. And so the probability of a union would be the sum of the probabilities. And each one will happen with probability 1 over 2 to the 4, but there's 4 of them, so that's how you end up getting that. Okay, so if that makes sense, let's do something that's a lot more complicated. Let's say we have a random walk up to time 20, and we want it to be equal to, so it has to be an even number. Let's say it's 8. How would we figure that out? So here's the way we do it. In order for 20 numbers, each plus or minus 1, to add up to 8, it means 12 of them. So 12, no, that's not going to work. 14. 14 of them are plus 1, and 6 of them are minus 1. So you can have plus 1, plus 1, plus 1, plus 1. That's 14 of them. And then we have minus 1, minus 1, minus 1. That's 6 of them. So in total, you have 20 numbers. And the position in the random walk, 12 minus 6, that would be 8. So that works out. So then the probability of that would be 1 over 2 to the 20. But then you have to multiply by how many different ways you can rearrange this, because this is just one way to happen. Now, if you know anything about basic counting, if you look at this list, there's 20 numbers in this list. And if these numbers were all, if these symbols were all different, then the number of ways you can rearrange that particular list would be 20 factorial. But you have a lot of repetition in this list. We have 14 of them that appear 14 times, and 6 of them that appear, and 6 of them that repeat, yeah, and these two repeat 6 times. So you really have to divide that out by 14 factorial, 6 factorial. So that's the way you would write that. And then you probably recognize what that is. That is the famous binomial coefficient that you write as 20 choose 6. Or you can also write this as 20 choose 14. They both work. So that's the way you would do it. So I'm sure you've seen this before. If you have never seen it before, then 20 choose 6, it's just a way you write this fraction. And it's symmetric. You can also write 20 choose 14 because you can interchange the 14 factorial with the 6 factorial. So now we can do this in general. Let's say this is Wn. And let's say this is I, where I is an integer between negative n and n. Then what would the probability be equal to? Well, based on this reasoning, this should be 1 over 20 to the n. I'm sorry, 1 over 2 to the n. And then this would be n choose, Now it's not choose I, because when the number is 8, it becomes 6. Rather, what you have to do is, if you think about how this works, you're taking 20, you're subtracting 8, that leaves us with 12, and you take half of them because they come in pairs. So this is really n minus I over 2. That's what it would be. And you actually get to see the reason why this integer has to be even or odd depending on whether n is even or odd. Because if they're both even, then their difference is even, and this is an integer. And if n is odd and I is odd, then their difference is odd, and their difference is even, so when you divide it by 2, that's an integer. You can also write, if you want to, that's actually the same thing as writing, maybe some of you spotted this, maybe some of you have spotted that this is n plus I over 2, 1 over 2 to the n. That's actually the same thing, right? It's just like what we had before. This is the other way you can write it. So we can therefore well, maybe what I should do is I should probably mention that, so maybe to summarize, Wn takes integer values, I, where I is between negative n and n, and I is congruent to n mod 2. And the probability that the random walk at time n is equal to such an integer is then given by n minus I over 2, 1 over 2 to the n. So that's what we're getting. Now, this probably should remind you of what they call the binomial random variable. So in probability theory, you might have seen what they call the binomial distribution. I'm going to call it the binomial random variable. And the binomial random variable, let's call it Bn. The binomial random variable is, so keep in mind, Wn is a sum of independent x's where each x is plus or minus 1. The binomial random variable is instead the sum of independent y's where each y is plus or minus 1. I'm sorry, 0 or 1. And in an undergraduate probability course, you think of these as successes and failures. You're counting how many successes you have. So when you add up zeros and ones, the amount of successes, you're sort of counting how many successes you had in total. So then Bn takes integer values, I, where I is between 0 and n. At the very minimum, they're all 0, and at the very maximum, they're all equal to 1. And the probability that this, what you call the binomial random variable, you do not say time n, you call them trials. You say how many trials took place. You think of a trial as how many attempts you've made. So Bn is equal to I is equal, so the way you calculate that probability, it's, now the way you have seen it, so this is probably the way you've seen it. So you write n choose I, and then you probably recall something like this, p to the I, 1 minus p to the n minus I. That's the way they teach you when p, this is the probability of one individual success in n trials. And there, p does not need to be a half. But what we're doing is we're assuming the probability of success and failure in each individual trial is equally likely. So this is a half, and this is 1 minus a half. So they both are the same, and the power is n. And so you would end up with 1 over 2 to the n. So it's actually very similar to what we're doing over here, except here it's slightly adjusted because we're working with plus and minus 1, whereas here it's a little bit simpler because we're working with 1s and 0s. But when you're thinking of random walks, this is the way you want to think about it, because then you're moving between positive and negative numbers to the right and to the left equally likely. Okay, so if you're looking at this and it feels very familiar to you and you're thinking to yourself, I feel like I might have seen it before, this is the way you've seen it. It's almost the same thing. It's just the notation is a bit different. Okay, the next thing that I wanted to say is this. Let's finish with this proposition. The expectation of a random walk up to time n is equal to 0. The variance at time n is equal to n. And the standard deviation is the square root of n. How do we prove it? It's actually very simple. I'm going to put it on the homework. But the basic idea is you want to go back to how the random walk is defined, that it's a sum of independent random variables. So then the expectation of Wn is the sum of expectations. And then you have to show the expectation of these is 0. The variance is n. Now, the standard deviation is by definition just the square root of that. So you have to work this out. But this is where you're going to use the fact that these are independent, because then the variance of the sum is the sum of the variances. So you just have to show that. But I do want to just intuitively explain these two. This should make sense because of symmetry. A random walk, it begins at 0. And then it could move to the right or to the left with equally likely probabilities. So intuitively, it makes sense that about half of them are moving to the right and about half of them are moving to the left. So you expect to remain at 0. However, as time increases, the variance is supposed to measure the spread, how spread out the random variable is. And if you think about it, a random walk up to time 5 can only move between 5 and negative 5. You have to be contained within that interval. So the spread is not that big. But if you go up to time 50, the spread of the random variable becomes a lot bigger. So it takes over a larger interval. So it makes sense that as time increases, the variance increases. And you're asked to just justify the exact calculation for that one. And with that, we have concluded our introduction to what a random walk is. And we're going to see some interesting theorems about them to follow in the new lectures.